who am I? First question you probably are asking. When I was talking with some people here, and there's a lot of people from academia, and they ask, so you dabble with Idris. Are you from St. Andrews or like the academia in general? So I started introducing myself as a rogue industry person. So an industry person gone rogue that's trying like things outside of the industry a little bit. But then immediately a friend of mine came up with a better name. Literally immediately, just 2 minutes after, independently typed. And I think it's my new Twitter name. So this is Germany. And it's Cologne specifically. And in Cologne, this program called A2LL was a software project that started to manage unemployment payments. So quite a sensitive thing. And by the 1st of January 2005, it shipped with a lot of deadlines, like late nights. And it was due to send 1.3 billion euro to more than 2 million households in Germany. So quite a big project. And the problem is, before the first payment was sent, there were some problems. German account numbers are 10 digits long, but some of them are a bit shorter. And you're supposed to pad them with zeros to the left, like you would do with any number. But the system was padding with zeros to the right. So some of the account numbers were invalid, and they never got the payments. Cool. We're talking about unemployment checks. Like, it's important to get these people need them to live. But it was a bit of a scandal, and the government issued some emergency cash so that people could eat. Then they started printing checks instead. They said, "Oh, the system doesn't work with these transfers. We'll just print checks because checks always work." And the street name in the form for the address, the validation was too short, and some German street names are very long, as you might imagine. So they got truncated, and some of the checks never made it either. By July 2005, the system had been running for 7 months, and they found several bugs, among which, for example, the system had been registering the users incorrectly with the insurance companies. So that was a massive headache for the insurance companies, a lot of bureaucracy and extra work. And then by September, 9 months after, they found the mother bug. So the bug was that the system had been transferring 25 million euros a month extra to the insurance companies. That wasn't really good, so the government said, like, we need to shut this down. Like, this doesn't work. And that was the end of it. This is Knight Capital Group, which in 2012, it's an investment group that lost $440 million in 30 minutes. And how they managed to do that is the system started buying stock high and selling it low. So that obviously was bound to not work at all. You already know this. In 2014, Apple go to fail. Yeah, well, the magic of not having curly braces in if statements. Yeah, doesn't need much more introduction. Heartbleed, I'm hardly the first person to talk about Heartbleed in this conference. And one of the consequences of it is that 900 social insurance numbers were stolen from the Canada Revenue Agency, thanks to this bug. And also, by the way, in OpenSSL, between 2006 and 2008, the random number generator was broken. So who knows what else hackers have done with this stuff. But bugs are not only about losing money or sort of disclosing sensitive information, which is bad enough. Some bugs are way more terrible than that. This is Panama City, and between 2000 and 2001, a radiotherapy machine in a hospital started emitting more radiation to patients than it was advised. And these patients went over a year of treatment, and 17 of them were dead because of overexposure to radiation. Toyota, if you've heard of Toyota unintended acceleration, it's a very self-describing bug that makes your car just start accelerating for no reason, and you can't override it in any way. So between 2000 and 2010, this bug caused 89 dead and 57 injured, and it was a big scandal for Toyota. This is a Spanair plane, which in 2008 It tried to take off, but some systems weren't ready to take off. And they would have learned that, but the monitoring system was hijacked by malware. So they never learned about that. They took off and they immediately crashed, killing 154 people. So I'm preaching to the choir here, but my point is correctness matters. It does matter. It's no longer about being efficient or having more elegant programs or anything like that. It's really, software is in our lives and it's only going to be a more important part of them. So correctness does matter. The first question that we should ask is, why are there so many bugs? Is it because we don't know how to program? Maybe. Or because our processes are not ideal, or they're deficient, or our tools are not great? Well, because I'm not a very good craftsman, I'm going to start blaming our tools. And the main tool that we use every day is our programming languages. And when I say our, I mean the mainstream, sort of most people's programming languages. They're very primitive. And they require a lot of discipline and cognitive power. The problem is our processes, however well-intentioned, they can't enforce discipline. They can incentivize it, but they can't really enforce it. So, that's not really good enough for our users, like just an incentive to do well. And when it comes to cognitive power, our brains are very easily overloaded, and we have a lot of trouble thinking about probability and other kinds of sort of things. And one of my favorite bugs in the brain, it's called illusion of understanding. And that's something I'm victim of all the time when programming, which is you look at a complex system, maybe an architecture diagram or a piece of code, and you feel, I get it. I've read it a little bit, and I know how it works and how the pieces fit together. And I could maybe rewrite it. That's the first thing you think. Oh, yeah, I'm going to rewrite it because I already understand it. Or I could build another one, I don't know, a similar thing. But then it turns out that it doesn't work. And you were really, really convinced that you understood that thing. So I could point you to lots of research papers about this issue of illusion of understanding, but I think the best thing I can show you is an art project by an Italian artist. I think his name is Gianluca Gimini, I think. He made the Velocipedia. How many people know the Velocipedia? Yes. Well, in the Velocipedia, this artist asked a bunch of people from different ages, different backgrounds, to draw a bicycle, a common object that everyone has seen, owned, and basically it's just a common object. Everyone knows it. So everyone was really confident that they could draw one. So they drew one, and it's like, yeah, I know how it works. And then he turned these drawings into 3D renders. And the funny thing is that the 3D renders show so obviously that these bicycles could never work as bicycles. And here's one example. This bicycle cannot have a human being on top of it. It just won't work. This one is pretty nice as well, with the frame sort of being crossed over like this. Pretty cool. But my favorite by far is this one, with the whole frame on one side of the wheels. And the double chain, of course. It's pretty fun. Check out the Velocipedia, it's really fun. And it teaches a lot about our flaws as human beings. Another problem that we have when writing code is that we scatter it with implicit assumptions. We have them in our head. Maybe we don't even know that we have them. And they're hard to remember because you're not really aware that you're having these assumptions. Then obviously they're even harder to communicate to your peers because they're just, you consider them shared context, but they're not shared. And many times they're just plain wrong. So you're convinced of them, but they're wrong. And they prove you wrong at production or at 4 a.m. So it's not the best time. So many of our languages are based on the Turing machine, which is this theoretical computation model that, yeah, it can compute everything that is computable, but it is very primitive. And it doesn't give us a lot of tools to think about programs and reason about them a little bit more formally. So I consider it a double-edged sword, and I'll come back to this later. But of course, we're at Lambda Days, and we know there's a different tradition called the Lambda calculus, yay, which opens up many more possibilities to leverage more of a systematic reasoning about our programs and stemming from the simply typed lambda calculus. There's type theory based on logics, and there's a lot of tools to think about programs that Turing machines maybe it's just not developed enough, the theory around them, maybe. I don't know. So how many people here use typed languages every day? Fair amount. And keep your hand up if you also write theorems and proofs every day. Okay, well, I'm going to prove you wrong. No pun intended, but you should have kept your hand up, all of you. The reason being, these two gentlemen, Curry and Howard, two talented people, happy in different degrees, and they came up with this, they discovered this, this fact that two different families of formalisms, on one side proof systems and on the other side models of computation, were equivalent. There was an equivalence, one-to-one equivalence between one and the other. So to understand what this means, let's review a little bit of propositional logic. Propositions A, B, and C, they stand for statements to say it's raining or I'm happy. Conjunction, it's raining and I'm happy. Disjunction, or an implication is if it's raining, then I'm happy. So this is very basic. But we're very interested in a flavor of logic called constructivist logic, which comes from a flavor of mathematics called constructive mathematics. And the difference between that and normal mathematics is that in constructivist mathematics, you can only prove things by construction and never by contradiction. Which means if you want to prove that an apple exists, you need to come up with an apple and show me. If there's no apple, then I can't, it's not provable that it exists. Whereas in normal mathematics, you could reason your way around it and say maybe, well, if an apple didn't exist, then this bowl would be empty, and this bowl is not empty, so an apple must exist. So in a way, this fits really nicely with our models of computation because, because we're interested in creating things and passing them around and sort of having these values pass around. And these are really proofs, but we'll see that in a minute. So this is the Curry-Howard correspondence. It's, I mean, I guess it's a bit longer than that, but this is the essence. Types are propositions and programs are proofs. So, for example, a type integer is the proposition an integer exists. And a program of type integer, let's say the number 8, is the proof that an integer exists. Because if you have the number 8, then an integer exists. It's obvious. Yeah? So this simple idea turns out to be really, really powerful. Let's have a look, for example, with more real things like apples. So this type apple means an apple exists. And for every different apple I can make, that is a different proof that an apple exists. So if I made 100 different apple values, those are different proofs. And all of these, in our type theory, they would type check. Because it's true that this apple is a proof of this proposition. It gets more interesting with function types. A function type is a claim that if an apple exists, then a list of apple slices exist. And so it corresponds to implication. The idea behind this, though, this seems like a bit far-fetched. Like, it's not automatic that if an apple exists, a list of apple slices exist. So the proof that this is true is the process of slicing an apple. If you couldn't come up with a process of taking an apple and slicing it, then this would be unprovable. It wouldn't be provable. But of course, it's probably pretty easy to slice an apple, and then this function would type check. So this is a very, very powerful idea. Basically, it means that types can represent arbitrary mathematical propositions. And if you supply a proof or a program of these propositions, your type checker can check that you're right, that the proof is right, and convert it to executable code, and then run it. So then you have a program. If this sounds like a more principled foundation than shifting around bits of memory and incrementing a program counter somewhere, I don't know. It's not for me to say. But the future will tell, I guess. Now there's a catch. There's more than one catch. But this is one of them. Our types, if they're too vague, then they're no good. Because they are very, very vague propositions that are really easy to prove with practically anything. So we really want them to be very precise. And we reach this precision through the concept of cardinality. So a type has cardinality, which is the number of values that it has. And here's a claim that higher cardinality leads to more bugs. Why? Because a type such as int, for example, a 32-bit int has 2 to the 32 different values, which is over 4,000 million values. And all of them will type check. But you're probably just interested in one value or a few values. So it's very easy to just come up with a wrong value, and it will still type check. A Boolean, for example, has two different values, and it's a slightly better type or easier to reason about. A string has infinitely many values because it could be infinitely long. And if you start with lists of things, then it just gets really crazy. So this I worked out the other day, and I don't know any math, so it's probably wrong, but it seems to work to calculate the cardinality of a list up to length n of x's, if you know the cardinality of x. And basically you can see that it's a ridiculous number. And usually lists are infinite as well, which doesn't, potentially infinite, so it doesn't really help. So let's see a more concrete example. So integer, 4,000 million possible implementations, string, infinitely many possible implementations. And this is just no good. So you better avoid using these types as much as you can. The lower the cardinality of your types, the easier to reason about. So how do we go about minimizing cardinality in practice in our programs, everyday programs? Let's take an example, slightly controversial example, which is appending two lists. This function appends two lists of ints. Or that's what the type claims. Now the cardinality of this is huge. Like, look at this. 2 to the power of 32 times infinite plus 1. This is a massive number, like massive. So you could come up with that many implementations of this function, basically returning an empty list, a list of 3 trillion ones, a list of 4 eighths, whatever you want. A list of random integers, why not? Let's try and improve it a little bit. So we have generics that help us a little bit because the appending list has nothing to do with integers. So we want to get rid of that and abstract the type into a type variable. And then you have this. Okay, so 2 lists of A's and it returns a list of A. That's slightly better. Slightly better. Not really that much better. Because you can still take the first element of the list, repeat it infinitely, and then interleave it with the second element of the second list, or whatever you want. And all these implementations are type check, but they're wrong. So yes, this is a bit of a problem. But we have another tool in our tool belt, dependent types. Let's look at how we would look with dependent types. So this would be this is wrong. List should be vect, which is an index list in dependent types. But you can see that it takes a list of n A's, n being the length of the list, and a list of m A's, and then returns a list that the length is n plus m. Now this is already way more constrained because you need to respect the length, and this still gives, you can have a handful of implementations that type check. Potentially many. But I'm going to show you something so that you're at ease with this. The idea is that if you get your types more and more precise, which with dependent types you can get to really extreme depths of precision in your types, then at some point the cardinality can be really low, even 1. So when the cardinality of a function is 1, there's 1 implementation. And the compiler can help you just write it out. You don't even have to write it. That's what happens in Idris sometimes when you're really good with really concrete types. So let's have a look, and I did a bit of exploration with Idris in this area, and I started with this function append. Yeah? So this is the correct implementation. Looks nice, elegant, really short, type checks, and it's also correct. Now I try to trick it and say, okay, I'm going to write an implementation that is wrong, but it type checks. So, for example, this is not really append, which just replicates the first element for the length of the list. It's doable, this type checks, but as you see, it's a little bit uglier, isn't it? I had to pull out these implicit parameters here and do a bunch of stuff. It's still doable, but, well, then I tried. What happens if you n plus m is supposedly the same as m plus n. So what happens if I just make a function that prepends instead of appends? That should be quite easy, right? Well, it wasn't that easy. So I tried to do this, and I ended up having to pull out two different proofs. One of them I called does a bear shit in the woods? It's right here, which basically, for two numbers left and right, it proves that left plus successor of right is equal to successor of left plus right, which for me is really obvious, but Idris didn't really believe it. It's really hard to bullshit Idris into things you think they're true. You have to always prove the stuff. So yeah, I managed to do it, but you would agree that this looks fishy. Like, this is not a ship it +1 pull request kind of thing. So that doesn't mean that always the correct implementation is the simplest and the nicest. That's sort of a coincidence. But in my short experience in Idris, this is the case that usually if you write really complicated code, it's probably not very right. But that's not true of everything. OK, so enough about cardinality. There's another thing that's, I think, quite powerful when it comes to correctness in our programs, and it's totality. It's another catch of the Curry-Howard correspondence. Yeah, so if you have a type, let's say a function of type that takes something and returns an int, and you know that the function is total, that is a pretty strong promise that that thing will return an int in a finite amount of time. But if it's not total, the promise becomes, look, if I ever return, I will return an int. Maybe I'll loop forever, and you will never know. You'll just wait. Or maybe I'll crash, and I won't tell you. I'll just crash. But if not, then I'll return an int. Don't worry. Well, that's not great. So you want your functions to be total so that your types actually promise what they are meant to promise. Now, if you take this idea to the extreme, you get to total functional programming, which is functional programming with only total functions. And yes, this sounds a bit weird. If Idris defines totality, it has a totality checker that obviously doesn't really check totality, because that would be equivalent to solving the halting problem. But it has some form of restricted totality checking. And if it can tell that your function will terminate, it will tell you, yeah, it's total. If it's not sure, it will say, no, it's not total, just in case. But it's quite smart, and it's based on this idea of termination and productivity. So sometimes it's obvious that a function terminates, doesn't recur, doesn't do anything, it just terminates. But sometimes it produces a finite prefix of an infinite sequence in a finite amount of time. That's still productive. It does some work, it returns. And you could call it again with more work, and it will keep doing stuff. So this is a valid use case. And in this case, the totality checker will agree with you. They'll say, this seems to terminate. It's a productive function. So that's fine. With these tricks, you can end up writing programs. Edwin Brady, the creator of Idris, has talked about running systems this way in some talks. And he even models servers, which are endless computations, let's say. So you handle a request and another and another and another. You never finish. He models it this way, basically as a stream of I/O actions. And then you just do a bit of work. And the trick is that then you end up with a program that's all total functions, except one function that gives it, let's say, the fuel. It calls it the fuel to keep handling requests, which is the only function that is not total. But that function is like this small, and you know what it is. So with this trick, you can basically write in only total functions, which is sort of equivalent to saying that you're really not programming a Turing-complete language. Because Turing completeness is overrated, I think. So you should give it up until it really hurts. And you really need it. Then you can use it. General recursion and all this stuff. So what happens if not everyone has a nice type system like in Idris, or like type theories are formal systems, and they have things that are not expressible in them. So some things you won't be able to express, or they will be too costly. Or you're using Ruby and there's no type system at all. So what can you do? Well, if if you can't reach it with math, science has always been there. It's pretty good. You approximate, you gather a lot of evidence, and you just approximate your, it's not going to be a proof, but it's going to be a lot of evidence that that theorem is true. That's what property-based testing is for, and I think it's a great tool that basically covers everything that you can't do in a formal system. So, as a bit of a recap, logic works. So you can rest at ease. And curving-out correspondence is a great way to think about your types and your programs. Explicit is better than implicit. That's really just preaching to the choir. And you need to aim for lower cardinality in all your types, because they basically constrain the number of implementations that will type check. And total functional programming is an interesting, if a little bit experimental, because as far as I know, there are not many languages that support that as a sort of first-class paradigm. Idris is one of them, and you should definitely check it out if you haven't. And, well, if all else fails, I've done that myself, you can design your types in a rich logic, such as Idris, or Haskell, or Scala, whatever floats your boat, and then port them to a sort of less expressive logic, where whatever language you happen to be working in. Or you can generalize a unit test into a property-based test, and it will make a lot of people happy. So there's a lot of ongoing research on all this stuff. This is quite, I wouldn't say new, but it's quite new. And the idea is to build more robust, predictable, and safe systems. Yeah, that's the goal that we share. So this is by no means the only way. And types are not the only way either. Testing helps, and you should keep doing it. But I think this approach is a little bit more systematic and very promising. That doesn't mean it's the best, but I think it's pretty promising and interesting. In any case, we can agree that if we need to build, the stuff tomorrow, the robots that will run everywhere in our bloodstream and everything, we need to do better than now. However it is, so we need to find ways to do better. And I think one of the ideas is to recognize that we don't know how to build software. It's only been 60, 70 years. And that's like nothing. So we really don't know much. And it's good to stay on the lookout for better ways of doing things, which I'm sure you have no problem with that sort of approach. So yeah, always keep an open mind and go build some nice software. Thank you.
Thank you. Now we'll have time for questions.
Hi. I would like to ask you if during your research you have seen some practical applications of dependent types, because as far as I've seen or Googled, I've only seen natural numbers and vector sizes. So there are the two examples which everyone gives, but I never seen any real application or use case. Thanks.
Okay. So first of all, I'm from the real world. Yeah. So I'm definitely not a researcher or anything. So I approach Idris from sort of a very practical, semi-practical perspective. And I think a great way, it didn't really click for me until I read this book, Edwin's book, which is really, really practically oriented, I think. And you start building projects that you would think, oh, I actually would build this in whatever my language of choice. And the things you can do in this logic are just crazy. This is insane. I didn't know this was possible. So I recommend reading the book, and I think that definitely gives you an idea of the really practical applications, including, for example, dependently typed state machines to model workflows and things that you think of as very stateful and things that you wouldn't necessarily think of dependent types for. But it's really great.
Okay. Any more questions?
Don't be shy.
Yeah, don't be shy. We have some time.
How do you deal with boundaries, where you have actually to, store your types in database or?
That's a great question. Great question. I had the same question, and this is also explained in the book. And basically, the idea is when you have to know something at runtime, like a user enters something, or you get something from some file or whatever. There's this boundary in which you make a decision. Like, for example, if you have index lists, you need to know that a list is of size 4, for example. So at some point you say, okay, I expect a list of size 4, a little bit like you're parsing something, and you say, okay, this is a list of size 4. And then if this is the case, then what you get is a proof that the list of size is of size 4. And if you don't, then you get a proof that it isn't. And from there, the type system can work. So you work with those proofs in the type system, and sort of this boundary from runtime to actual proofs that the type system will use is where the decision is made. So you still don't know what's going to happen at runtime, but you know whatever happens, you know all your logic is consistent with the case.
Can you give us some advice about how to convince people that are used to writing unit tests that property-based tests are good?
Well, I guess like I'm not the most indicated person to you know, like it's sort of a, yeah, I guess in our bubble it's a bit of a self-evident thing, but I understand that sometimes you talk to people, some of my colleagues maybe I think their problem is that, and my problem sometimes is that you can't really come up with a property that you want to test. So you haven't really thought about what you're testing too well, and what you have is a couple of ad hoc tests, and you know that those are supposed to be the thing, but you don't see the general property. And I think that's a bit of a problem, but the approach I've taken is if you can't see the property, then don't worry about it. Like when you write another test, it will hurt a little bit because you're writing a lot of tests, and you'll be like, oh, I think I see the property that I'm trying to test here, and these tests are just like ad hoc stuff. And then you generalize it only when you actually see it. But that said, it's also, I think, a matter of practice. The more property-based tests you write, the easier it is to think in terms of property-based testing. So it's a bit of a catch-22 situation. So I don't know what to advise you, but yeah, I don't know. Maybe talk to your colleagues, share some talks, and you know maybe they'll be convinced.
So I've been starting reading that book as well, and I'm probably equally excited about as you are. I've been wondering about one thing that I couldn't solve yet. Probably you can answer me that. When you do something like creating types from user input. Like one of the things that's really cool about Idris is that you can like read some machine readable schema, which is in a file, for example, in a type at runtime.
Yeah.
But that must mean that your types are actually visible at runtime, right? So normally in programming languages, when compiling, the types disappear. They're not in the compiled binary anymore. Do you know where is that border between the types that still exists at runtime in an Idris program and which don't? Something I've been thinking about and which I couldn't solve yet.
That's a very good question, and I had never asked myself this, and I think it's really interesting, but I have no idea how. So I guess you would have to ask some of the Idris developers. They probably could explain, and I'm interested in knowing how it works. Yeah, I never thought of this. Of course, some of these have to stick at runtime.